Thank you very much indeed. So, with apologies for the pun in the title, I'm here to talk about festive foods and the mathematics that can go into modelling them. So I'm going to sort of loosely work my way through a Christmas dinner, but it's very loose. You wouldn't really want to live on just what I've got on here. But let's start, well, with a roast ham. So I'm going to, for each of the foods that I discussed today, I'm going to be using different mathematical techniques. But for the roast ham, I'm going to assume, because I'm a mathematician, that it is a spherical ham. And actually, that's not a terrible approximation, right? How long do we need to cook our ham? So I've got a spherical ham. I'm going to assume that I've just taken it out of the fridge because I'm an idiot and I don't know about leaving these things out to come to room temperature. I will have preheated my oven, and I'm just going to look at the temperature within the ham. So I assume that the surface of the ham instantly gets to the oven temperature, and then I need the heat to slowly make its way to the middle. And I am told, having checked the internet, that the rule for cooking a ham is you cook it just enough. You only cook it just enough that it's safe. So you keep going until the middle reaches the temperature at which it's safe to eat the meat. And I've given all of those relevant temperatures names. So what mathematics do we need to do that? What we need is what's called the heat equation, funnily enough, for how heat moves about through things. And it says the rate of change of temperature with respect to time, that's the thing on the left, is a constant which I've called K, which is called the thermal diffusivity, tells you basically how fast heat travels through this particular substance, times this magic thing called del squared T. So that upside down triangle is called del. And it's a special derivative with respect to position. It tells you about things changing in space. In particular, if I have a spherical object and everything that happens within it has spherical symmetry, which if I've assumed a spherical ham and my oven is the same temperature all over, it should stay all spherically symmetric as I go on, then everything only depends on the distance from the centre, which I've called r because it's a radius, and time t. And the derivative ends up being this thing at the bottom of the screen, and my pointer isn't working because I'm never any good with pointers, but it's the big equation at the bottom, and it only depends on r. So I've got a derivative that I can write down that just depends on r. So that's the equation I'm trying to solve, and we can solve that one. We can solve it by separating variables, and that is the general spherically symmetric solution that I've written down. That is valid for all radiuses, radii, and for all time t. So now, how do I actually get something useful out of that? Well, what do I know? I need, initially, it starts out at fridge temperature everywhere. I need, at the outside edge, it's at oven temperature for the whole time. And I know those two things don't agree with each other, but gloss over it for now. And then in the middle, I need these things not to blow up. I don't want any infinite positive or negative temperatures anywhere because those are just really, really bad. So let's use that. We don't want any of my functions to go to infinity at r equals 0. Looking at my general solution there, I've put in red the ones that go horribly wrong when r goes to 0. So those red ones are not allowed. 1 over r becomes extremely large near the middle of my ham. I do not want that to be part of my temperature. The same thing happens with cos of something times r over r. The cos of thing is very much like 1, and so it blows up. The green ones, on the other hand, are okay. So we'll keep the green ones, but we'll throw away the red ones. And to do that, I take the coefficients in front of them, which are numbers I want to pick, and I pick them to be 0. So that simplifies my solution a little bit. It's got shorter. Now, I've still got an infinite family of these A's and an infinite family of these omegas to choose. So what do I do next? I use the condition on the outside, which tells me that the oven temperature is equal to this value when I put in the radius capital R. Now, that sine omega n capital R over R, that's just a number. So this thing is a sum of things, each of which, except the first one, depends on time. I want it to be a constant because my left-hand side is just the oven temperature, which does not depend on time. So actually, I need that first term, the A0, to match up and to be the constant, and I need everything else to be 0. Now, I could just set all the ANs equal to 0, but that's not going to leave me with much solution to play with. What I do instead is to fix the A0, as I said, but to get the omega ends to make the function 0 at the edge. And that tells me what my omega ends are. So each of my omegas is now n pi over r. And then I've just got one condition left, which is the initial condition that at time t equals 0, it's at fridge temperature. So that's my new solution. I now haven't got any unknown omegas. I've only got unknown a's. And I need the initial condition to define the a's. And for that, we use Fourier series, which I'm not going to go into the details of. Those of you who've seen them know what I'm doing. Those of you who've not seen them, they are brilliant and they are magic, but they take far too long for this talk. And you can determine what the numbers an have to be. There is a unique set of ANs that will satisfy that initial condition. And when I plug them in, this thing at the bottom has nothing left in it that is unknown. I now know the temperature at every point in the ham, at every moment in time, in terms of the oven temperature, the initial temperature, the diffusivity of the ham, and the radius of the ham. And that's all. So what can I do with it? Well, I need to pick numbers, obviously, so I've imagined that my ham has a 15 centimetre radius, literally just waving my hands in the kitchen and then measuring the distance between them. The rest of the information I've taken from reliable sources, so the diffusivity of ham is right, although there is a subtlety. Ham has a different diffusivity when it's raw from when it's cooked, and obviously it's going from one to the other in the course of the experiment, so I've just picked one of them. Fridge temperature is what it is. Oven temperature is what I was told to roast a ham at when I asked the internet, and safe temperature is what I was told when I asked the internet when is it safe to eat my ham. So 5 minutes in, this is what the temperature inside the ham looks like. It's basically at fridge temperature almost everywhere, except for a little layer near the outside. As time goes on, that warm layer migrates inwards. So an hour in, quite a lot more of it is warm. 3 hours in, the sum of the heat has got to the middle. After 5 hours, you can see that I'm starting to get somewhere close to my critical, you can eat it now, temperature of 57 degrees. So this is quite a big ham, and it's going to take 5 hours to cook. And yeah, maybe I shouldn't have left it in the fridge, and maybe 15 centimetres is too big for the radius of a ham. But anyway, we have an idea. So this is the temperature in the middle from the graph that I've just drawn. So I'm now just taking the temperature at the centre of the ham and plotting it against time. So in this case, there's my safe temperature. I need to wait until it crosses that line, which as I drew from the previous one, is actually 5 hours and 20 minutes for this particular ham. So that's given me a time based on a radius. I can now generalise that and go, well, let's look at a variety of radiuses and say, what's the cooking time that I need for each radius? And that gives me this graph. And what I want to do with that is just sanity check it. Does it give me anything remotely sensible? So again, I asked the internet and it said a 12 to 14 pound ham, helpfully, obviously I've done it in metric, right? 12 to 14 pound ham needs 1.5 to 2 hours. So this is the 12 to 14 pound ham range. 1.5 to 2 hours is that slice. So we're in the right ballpark. It could be a lot more specific, but then there's all sorts of things that we haven't included, like letting it come to room temperature, like the diffusivity changing as you go through the cooking process, like the fact that your ham is not actually spherical. So now we know how long to roast a ham, roughly. What do we do? What did we do? We made some simplifying assumptions, and with those, we found an analytical solution. And that's kind of the best of maths, when you can make your setup simpler and then just solve the whole thing. It's lovely. How specific is what we've done to ham? Well, it's not really, is it? Everything I did until I started plotting graphs was completely generic to heating up a spherical object. I didn't need to know it was a ham. There's nothing specific to the ham until the very end. And any system that has the same physics will satisfy the same equations. And in particular, this mathematics applies to all roast objects. So we get roast potatoes for free. And I'm afraid I'm going to move on from the savouries now. So next up, we have, and it's really not part of Christmas dinner, but it's definitely a festive food. Now we're going to look at Stollen. So this is a bread product. How do we make bread? Oh, yes. So unlike the ham, I didn't do this one by myself. So I need to give you my partners in crime, slime. Sally Everett, who was my PhD student, who really did the hands-on work here, and fellow supervisor Oliver Harlan, and a specialist in polymer things that we had to call in, Daniel Reed, all at the University of Leeds, as was I at the time. Those are the publications for anybody who's interested, and the funding came from Huntsman Polyurethanes and EPSRC. And you'll notice I've said the word polyurethane, which is not something you should ever get in bread. Nonetheless, it is relevant. So, what happens when you make bread? You need it to develop the gluten, which is a long, stretchy polymer. And that makes the dough elastic. Then you leave it to prove. And it's really that proving process that I want to look at. So during proving, the yeast ferments the sugars in the dough. And in doing so, it produces carbon dioxide, which forms first small bubbles, and then extra carbon dioxide that's produced in the dough diffuses through the dough into the bubbles, and the bubbles grow, and the whole thing gets bigger, and the bubbles stretch, and the gluten stretches, and you need the gluten there, otherwise you get burst outs of bubbles and a few enormous bubbles instead of a nice even texture, all of that kind of stuff. That process is exactly the same as what happens when you build a polyurethane foam. So you put reacting polyurethane in a mould, and the reaction produces carbon dioxide, which migrates into little bubbles which grow, and the elasticity of the polyurethane restricts how much they grow, which is exactly the same process that they use to make steering wheels. And a variety of other foam products, but that's probably the one you're most familiar with. You want a steering wheel to be strong but light. And yeah, they're almost always made out of polyurethane foam around something very structural. So Huntsman Polyurethanes sponsored us to look at the dynamics of polyurethane foam, and it absolutely does the same thing as Stollen. So I'm just going to show you what we did, because it's cool. So we're looking at another diffusion problem. This is diffusion of the carbon dioxide through the dough to try and get to the bubbles. We're actually solving the heat equation again, because it's also known as the diffusion equation. It gets everywhere. So I said that del squared thing was magic. It really is. It will keep on just, if you ever study the mathematics of physical things, it's coming for you. The other things we had to include, the pressure difference between inside the bubble and outside the bubble, the elasticity of the dough. So that's kind of, as you stretch it, it pushes back, it wants to squeeze in. Surface tension on the edge of the bubble, that will happen just the same in bread and in a polymer. And then as the dough stretches, its elasticity itself changes. So that's, for the bread, is more during the baking process, whereas in the polyurethane it's all happening at once, but it's still part of the process. And the reaction itself produces the gas. So what could we do with this? Well, actually, the governing equations for this one are quite a lot more messy than the ones I just showed you for roasting a ham. So you've got diffusion, which is easy, but then you've got a fluid flow which has elasticity in it, and a geometry that's changing, which is always a difficulty. So what we did, instead of trying to solve it by hand, we simulated it. So we went, okay, let's assume that we have a family of identical bubbles, and we want to see how they grow. What's the smallest element of that big family of identical tessellating hexagons that we can simulate? And to start with, you go, okay, I'll take one hexagon. But actually, no, hexagon's got loads and loads and loads of symmetry. You can do a much smaller bit than that. You can do a bit that small and replicate the entire thing out of it. So that's what we did. We took that little tiny segment, and you only need to do the bit I've put the thick lines around, because the rest of it's just a bubble of carbon dioxide gas, and that just behaves. You only need to worry about what's going on in the fluid bit. So we took that, and what we found was, as we simulate, that's the initial shape is the pink one, and then as time goes on, what you get is a high stretch in the middle of the bubble face. So that's the thin bit of our simulating thing. And then as the reaction finishes and everything goes solid, that stress relaxes. But you do end up with these, that high stress stops the bubbles from expanding as much as they would if it was an ordinary water foam. And you get quite thick walls between the bubbles. And actually you do observe those in bread, that the walls between bubbles are much thicker than you get in ordinary, like, sort of washing up water bubbles. So that was quite cool. We've got thin bubble walls, but not as thin as they would be if it was a proper water foam. And we've got these fat doughy corners in between where the bubbles meet. Now, those are all identical bubbles, but we'd like to do bubbles that are not identical. And we realised, after some considerable thought, that if you take 2 bubbles of one size for every 1 bubble of the other size, you can do this still in a nicely periodic way. So we could essentially stitch together 3 of our little bits to make that object and simulate that. And from the results of that, you can multiply it up to get the shape of the foam with 2 different sizes of bubble in it. And that's as complicated as we could get it. I never quite managed to do the full plethora of lots of little bubbles and lots of big bubbles and lots of medium-sized bubbles all at once. But from this, if we have a higher population of the big bubbles and only half as many of the little bubbles, what you end up with, and here it's very difficult to see what's going on if I just give you the little replicating element, so we've made the big picture out of it. You end up with very high stresses. You can't quite see, I don't think, the legend on that scale, but it goes up to 40. Large stresses in the windows, in the windows that get very thin and are being pulled apart quite rapidly. And it's quite an open foam. There's a lot of gas for each bit of fluid in there. Whereas if I have lots of little bubbles and only half as many of the big ones, the other way around, I end up with much chunkier pieces of dough in the corners. And the index on this one is only 20, so the overall stresses are much lower, which means that everything's not getting as stretched, which obviously has an effect on the texture of the foam that you end up with. I haven't really shown you the maths of this because you don't want to see the guts of a numerical simulation. That's not festive. But what have we seen? We've seen the heat equation and an awful lot of other bits of physical modelling. Again, we made simplifying assumptions. For a start, I made it 2D, but then I made it a hexagonal pattern and all sorts of things to make it tractable. And then we found a computational solution this time. How specific is it to Stollen? Well, it's really not, because I got it from polyurethanes, which are absolutely not Stollen. And so again, I'm using exactly the same line again. Any system with the same physics obeys the same equations. And this is the universality of mathematical modelling, that you can take the equations and they are going to apply everywhere that that physics applies. Right, my next subject is not Christmas pudding. I don't think there's a lot to really model in a Christmas pudding. It's the custard. And that's fine, but that's not what custard looks like at the beginning, right? Looks a lot more like that. And that's what I want to talk about first, because this is raw custard or cornstarch, basically, with some flavouring and sugar in it. And it behaves really, really weirdly when you first mix it up. Again, I have partners in slime on this one. So Yurian was my postdoc, and we worked with people from Edinburgh and Cambridge on this work. Yurian was sponsored by an EPSRC grant called Coral, about complex formulations for oral health. So we were supposed to be studying toothpaste, But we ended up studying custard because of this universality of mathematical modelling, right? Some of the things that go into toothpaste behave quite a lot like custard some of the time. And again, there are the references for anybody that's actually interested. So, what am I talking about? Custard powder is mostly, certainly in the important bit of what it does, corn flour. And this is a micrograph of corn flour on the right. They're basically spherical particles, right? We're going to make that assumption again. Identical spherical particles every time. And they're really, really close together. And there is liquid in there because you've made a cornstarch and water suspension, or possibly milk, but for the purposes of modelling it, it's a liquid. That's all you need to know about it. But there's not much of it in there. It's almost all corn flour. And that was, some of the audience are too young to know who he is, but some of you are not. Who is it? Jonathan Edwards. And he was running on custard powder for Blue Peter to demonstrate that you can. So if you make it up, it is a fluid. You can stir it, you can pour it. But if you're quick enough, you can run across it. Right, so it's made of all these tiny little spheres, many of which are in contact with one another. And you can simulate, you can do a computational model where you actually track every particle and see which two are in contact and add the force between them. It's hugely computationally intensive. So for big applications where you need to use these things at more than tiny scale, you really need a model. You need something better. And what I'm going to talk about here is the process of creating the something simpler. So we start from an observation that the most important thing for the dynamics is the contacting pairs and the interactions between them. And so we need to have a way to predict when a contacting pair is created and when it is destroyed. So, if you zoom in close enough to a particle, you can assume that the flow field around it is linear. So what I mean by that is any variation in its flow just depends on how far away from it you are. So it might be moving with a constant velocity and all the stuff around it moving with a constant velocity. That's fine. Just change your frame of reference to go with it. What you care about is whether things are being brought towards it, and those can be done in a way that is proportional to how far away they are from it. That means that I can write it as the local velocity field is just a matrix times the distance vector. And I'm going to split up that flow gradient tensor. It's actually a tensor, not just a matrix, but that doesn't matter if you don't know what a tensor is. Into three components. Omega is the rotational bit, which does everything that goes around. So that's not going to move things in and out of contact. It's going to move them around in a circle. EC is the compression bit, so that's what moves things towards one another and creates pairs. And EE is the extension bit, which moves things away from one another and destroys pairs. How do I identify those? Well, the rotation matrix is easy. It's the part of the matrix that is antisymmetric. So I can split it into the antisymmetric and the symmetric bits, and the symmetric bits has to be the two E's somehow, and the antisymmetric bit is omega. So that's dead easy. And then I look at the rest of it and I separate it out into the component that has negative eigenvalues and the component that has positive eigenvalues. And that, it turns out, is unique, but let me give you an example. So a very common flow is shear, which is this. So the velocity at a point here depends only on my height, and it goes sideways at a speed that's proportional to height. So if it's down here, it's going really slowly. If it's up here, it's going really fast. So I've got this sort of action going on. That's represented by this matrix L. And if I split that into its symmetric and antisymmetric parts, the antisymmetric is given there as omega. It's got half gamma dot on the diagonal and minus half on the below the diagonal. And then the sum of the E's has to be the other half of L, right? So it's got half gamma dot above the diagonal, half gamma dot below the diagonal, and nothing on the diagonal. And when I split that up into the components with positive and negative eigenvalues, this is what I get. So these are, they each have one non-zero eigenvalue and one zero eigenvalue. And essentially EC is a matrix that brings things together in that direction, and EE is a matrix that takes things apart in that direction. And what we see then is that as my flow is going, if I've got a test particle in the middle, if a particle comes in from over here, it'll get whooshed along, it'll get brought into contact, rotated around, and then taken out of contact again. That's how the dynamics works, and that's what those three matrices do. From that insight and that building block, we can now create a model. So P, for anyone who wants to know about the technicalities, P is the unit vector along the line of centres of a contacting pair. And I define A and B as the average of PP and PPPP. And I can deduce how A evolves with time in terms of my matrix, actually the whole matrix L and the extensional and compressional components of that matrix. You need a closure relation between A and B, which we were able to source from the literature. It's been around for a good 20 or 30 years. And you need a way to extract fluid stress from everything you've just got about the microstructure. But essentially, this tells you how the microstructure evolves. And from that, you can then build a whole model for how the whole fluid behaves. So that was quite complicated. And it was an awful lot more complicated as we were doing it live. It took several months. And all we've ended up with is a bunch of equations. When I did the ham, we started from the bunch of equations and then we did all the work. But sometimes in mathematics, the challenge is finding the right equations to solve in the first place. And once you've got them, you just go, give it to a computer, it's fine. But the computer can't do this bit, can't do the designing the equations. That's got to have human creativity in it. So we didn't really want to talk about raw chocolate, right? Raw chocolate, raw custard, because you don't want to eat that. We want to talk about cooked custard, and here I am going to cheat, because I look at custard flowing down a Christmas pudding and I go, that looks a lot like chocolate fountain flowing down a chocolate fountain, specifically that bit. So now I'm going to talk about the chocolate fountain for the rest of the time, even though it's not really a festive food, but we're just going to sort of pretend that it's custard, right? So if I want to muddle the chocolate fountain, oh, hang on, I've got a partner in crime on this one as well. So Adam Townsend did a fourth-year project with me as an undergraduate, and that was the chocolate fountain. He since then has done a PhD with me on the suspension mechanics, so essentially on the raw custard, done a postdoc at Imperial, done a postdoc, he did a short postdoc with me as well, and he's now a lecturer in Durham, so it's gone really well for him, but this was right at the beginning of stuff. So there is a publication, but also we managed to get it to come out just before Thanksgiving when all the papers were looking for a silly story that was to do with food. So it got picked up by, that's the original paper, but it got picked up by the Mail Online. And even the Washington Post, with its fantastic headline, someone finally looked into the physics of chocolate fountains, because we've been waiting for that forever, right? It was really needed. Right, okay. So what do we model when we're modeling a chocolate fountain? Essentially, there's two components, right? The chocolate and the fountain. So I'll talk about them both in turn. So the chocolate is a complicated thing. It's got sugar, it's got cocoa solids, it's got cocoa butter, and the cocoa butter varies every year according to the quality of the harvest. So you think you've modelled chocolate perfectly, and then next year's chocolate is different. So chocolate is a real mess. So instead of trying to model it from first principles like we just did with the custard, what I'd like to do with the chocolate is just go, no, let's just measure what it does. How do we do that? So I talked earlier about shear flow. This is the idealized shear flow, which I finally now put up a diagram for. You apply a stress, that's essentially a force, that way along the top, and out of it you get a rate of strain. So you get a shear rate, which tells you how fast it is, basically that velocity divided by that height. And then you can define the viscosity, the thickness of the material, by just dividing the stress by the shear rate. And in practice, this is done in usually a Couette rheometer. So you rotate the middle thing, and you can see where the chocolate is. The thin layer of chocolate between the inner cylinder and the outer cylinder undergoes a shear flow, and you can measure the torque that you have to apply to make the inner one go round, and that gives you a measure of the viscosity. So having done that, what sort of shapes could you get? Well, I've classified them all here. So this is stress, so essentially the force, plotted against rate of strain, so essentially the speed. And I've got 4 curves here. Let me talk about them each in turn. So the Newtonian line, this is the straight line. It's called Newtonian because it goes back to Newton. This is the simplest fluid, and fluids with a really, really small, simple microstructure are all Newtonian to a good approximation. So water, not babies, wine, honey, and air. And you can imagine, with water and air being in that category, there's quite a lot of study of the Newtonian fluids equations going on, because that's how all the weather forecasts work and all the climate prediction, and, you know, it just goes on. Right, shear thickening. So this means that the harder you push it, the thicker it feels. There's not very many of these, but we have seen one already, the cornstarch thing. So this is somebody running on a swimming pool full of the stuff. But it is still a liquid. I mean, you can see it's got waves on it, right? It's definitely a liquid, but he's nonetheless running across the surface. And custard, as already mentioned. They are creating bulletproof vests out of this stuff. You can get Kevlar infiltrated with cornstarch, and it becomes much more bulletproof, because in the short-term impact of the bullet, the cornstarch molecules do their I'm being really thick, I'm going to act like a solid thing, and shatter, taking all the energy out of the bullet on the way. But when you're just wearing it and bending down to tie your shoelaces, they go, oh, no, this is all slow, this is fine, I can bend, I can let you see your shoelaces, unlike the ceramic plates that they used to use before. So that's really quite cool. Right, the next one, Bingham fluid. So what you will notice about this one, actually the fact that it's a straight line is not the important thing. The important thing is that it hits the y-axis above the origin. So you can apply a finite stress to this stuff and have it not move. This is what's called a yield stress, and it means that for small amounts of force being applied, nothing happens, and then at some point it flows. And you have seen things like this. There's one. You know, if you just hold the ketchup bottle and just hold it, it just sits there. You have to actually do something to get it out. Probably the best thing to do, if you have the coordination for it, is to rotate the bottle like that, because that applies a sideways stress, which is enough to release it, and then you only get gravity pushing it downwards, so you get a controlled flow of ketchup instead of the dollop that you get when you hit it on the bottom. Another one is toothpaste. So this brings me back to my coral project, right? So one of the things that they wanted to do when they sponsored us to look at toothpaste, they were trying to move from batch manufacturing to continuous manufacturing, but they were also trying to stabilize their batch manufacturing. So what they would do is they would take this huge vat and make 50 tons, I think it was, of toothpaste in one go, in one big mixing experiment that would take kind of 2 days because of the length of the stirring. And then it would come out, and mostly it would look like that. And now and again, it would come out runny. It would come out without the yield stress. And all of the right ingredients were in there, so it would still work fine as toothpaste, but nobody would buy it because it didn't feel right. And so they had to throw away 50 tons of really good toothpaste ingredients because it just wouldn't sit right on the brush. And they wanted us to identify what was going wrong and tell them what to do to avert it. I'm not sure we managed it, but we had to go. Right, and then the final category is the one where it bends down. So the faster you push it, the thinner it feels. And there's quite a lot of these. So paint is designed to be shear thinning. So it doesn't dribble all over the floor while you're going from the pot to the wall, but when you're brushing, which is a fast flow, it allows you to brush it smoothly. And then when you stop, it thickens right up and does not leave the wall before it has had time to dry. So that's designed in. Lava, not so much designed in, but as it happens, just the same stuff. And the reason, of course, that I put it here is that chocolate is another one of these. So here I have a graph of the viscosity of chocolate plotted against the shear rate. So this is now not stress against shear rate, this is viscosity against shear rate. You can see that the viscosity is getting lower the faster you shear it. You can also see that white chocolate is thicker than milk chocolate and milk chocolate is thicker than dark chocolate, and who knew that? Right, so we've got a shear thinning fluid. How do we measure a shear thinning fluid? Not measure, we've already done that bit. How do we model a shear thinning fluid? Well, I've got 3 really simple fluid models here that have routinely been used for chocolate. Newtonian fluid, the power law fluid, and Casson's model. So first of all, the Newtonian fluid. We can just pick a sort of average viscosity off that curve. And Newtonian fluids have been so well studied that it's always worth doing the Newtonian fluid as a sort of test case. So that's sort of always in your armoury. Then there's the power law fluid. And we can fit those equations reasonably well with a power law of a third. So that viscosity goes down like x to the power minus 1/3. And then Casson's model, which is pretty complicated. It's particularly complicated because it's got these 2 different square root bits in, which apply for very low shear rates. It was the accepted model by the International Confectionery Association from 1973 to 2000. It's very specific. In 2000, they looked at it and they compared it to the data and they went, it's really complicated and fiddly to deal with around very small shear rates. It's also not very good at very small shear rates. So henceforth, we recommend that you use an ad hoc model, by which they meant use the power law fluid and use different segments of power law fluid in different bits of your flow if you need to. So that's what we're going to do. We're just going to use the power law fluid. I might refer back to the Newtonian fluid for comparison purposes now and again. Right, so we've modelled the chocolate. Now we need to model the flow. And we looked at a pumping flow, a dome flow, and a falling sheet of chocolate when we did the project, but I've only got another quarter of an hour, so I'm only going to look at the dome flow today. But you can look at, no, you can't really look at the pipe flow, it's inside, but you can certainly look at the curtain flow later on. So, simplifying assumptions. I'm going to assume that we're working in 2D, just because it makes it a tiny, tiny bit easier. To be honest, that's an assumption we shouldn't have made. It didn't make it that much easier, but having made it, I'm not going to redo the calculations. So this is a cylinder now. We've got a cylindrical chocolate fountain and stuff's flowing down the sides. And that's the way I've set up my geometry. So capital R is the radius of the dome, and H, which depends on theta, the angle down from the top, is going to be the thickness of the fluid. Right, and we know the governing equations. These are the general equations for any fluid flow. The first one is the fluid equivalent of forces, mass times acceleration. The forces are on the right as it happens, and the mass times acceleration is on the left, but that's still what it is. We also have the second equation there is conservation of mass. It says that however much chocolate you've got, you keep that much chocolate. And again, I need some more simplifying assumptions. So I'm going to assume that if I'm flowing down the dome, I never start going that way or that way. Everything stays within the plane. The flow variation also stays within the plane. I'm going to assume that it's been going long enough that I'm looking at steady flow. So I look at the long time flow, not the beginning bit. And the least debatable of those assumptions is that gravity points down. With those built in, these are my governing equations. There's a bit too many of those. We'd quite like to make things a bit simpler than that. So I would like to see if any more quantities can be made zero. So let's have a look. What do we have? I can fill in what all of my stress components are in terms of the flow, and I made some assumptions already about which way the flow might point and which way its variation might happen. I can deduce some things at the bottom about things that are zero, right? So I've got a whole bunch of 5 different stresses that I know are zero. That's got to make my equations better, right? Substitute them in. All of that red equation is zero. Nothing else changes. So that's not very satisfactory, except, of course, I will get rid of that one. So we've made it a little bit smaller, but only a little bit smaller. I need to do something cleverer. So what I'm going to do is I'm going to look at that bottom equation, which only has 2 terms in it, and I'm going to do something really clever with that and with my geometry. So here's my geometry. I've got a big radius and a small chocolate depth. And I think we can all agree that not just on this slide, but in reality on the chocolate fountain, the thickness of the chocolate is much smaller than the size of the thing it's flowing over. That's going to be what I use. So let's scale the velocities along with capital U, the velocities up and down within the film by capital V, distances within the film I'll scale by the film height, and radiuses I'll scale by the big radius. And that tells me that my quantity u theta looks like capital U, my quantity u r, which is the radial velocity, looks like capital V, the height looks like capital H, radius looks like capital R, and the variation d by dr, derivative with respect to distance, well, any variation has to happen over this thin gap. So that looks like 1 over h. If I put all of those into that last equation I had, which was this one, what I have is the first term is of order r times v divided by h, and the second term is of order u. But if I've got an equation that says a plus b equals 0, then a and b have to be the same size as each other, with a minus sign, obviously. A and b are the same size. So if one of them is order 1, the other one also has to be order 1. And what I've got here, I've said I now need that r times v divided by h has to be the same size as u. And h is much, much smaller than r, and that tells me that v is much, much smaller than u, which tells me actually that any velocity along through the film, up and down, is much less than the velocity along. Basically, it's mostly going down the dome, and there's only a little bit of up and down. It's not a surprise, but I've formalised it, and I know exactly what I'm discarding if I throw away anything that's smaller. Using that argument and other similar arguments to tell me that some terms are smaller than others, I can now say that all of those red terms are smaller than other things that they're in the equation with. And that really does make my equation simpler. The bottom equation I've sort of used now, so I can get rid of that. I'm just left with these two. There's not much in there. There is P, which is my pressure. So I've got a pressure gradient. There is gravity. We were expecting gravity to still be there. And there are fluid stresses. What I've got is a balance between the pressure and the gravity together, which are the external forces pushing the thing, against the fluid stresses, which is the viscosity. It's a balance of gravity and viscosity, and that's the only thing. The only bit of geometry that is still there is the cos theta and the sine theta attached to the gravity. That just tells you about the slope, the local slope. So what you get at the bit of film where we're at angle theta is exactly the same as what you would get if the entire thing was a plane at angle theta. Everything is just in the slope. And those equations are called the thin film equations, and they apply everywhere that you get a thin film. So I found a paper that was doing lava flow down a cylindrical hump of, I guess these things do happen, right? When there's a crack, you get something that has a long length but has things going down the sides. So the cylindrical volcano with lava flow going down it had been done and has exactly the same structure as this chocolate thing we've done. There are many industrial coating flows where the size of the flow is much greater than the thickness. Tear films in your eye are much thinner than they are wide. And so these equations get everywhere, again. So we can solve them because they're so simple. It's a bit messy. It's got 5/2s in it and stuff, but it's not impossible by any means. And if I plot it against the depth to look at what the velocity is doing, I said I was going to go back to the Newtonian one. So you can do Newtonian as a special case of power law. You just pick your n to be equal to 1. So on the left, I've got what chocolate really does with the power law. And on the right, I've got what it would do if it was Newtonian. And the difference is that actually you get a much more efficient flow with the chocolate. You end up with a layer close to the dome that's got quite a high shear rate and is therefore really thin and sort of lubricates everything else, and then more or less a plug flow on top where you just get a wodge of chocolate that's moving along without having to feel any flow at all. Relative to the Newtonian, where the shear variation is distributed throughout the layer. And we can predict the film thickness from that. And this is not a decent scientific comparison because all I had was a photograph taken from a birthday party of what the film actually looks like, and then another photograph taken with the chocolate fountain with no chocolate on it. And they're not necessarily quite to scale, but it doesn't look terrible, the film thickness. It's sort of believable. So let me review what we've done. Yet again, it's always the first thing I say. We made simplifying assumptions. This time we introduced scaling analysis. That's the name for this system where you look at terms that are much smaller than other terms and throw away the small ones. We discarded the small terms, and as a result we found an analytic solution. So we're back to the roast ham levels of success. We actually were able to solve the equations in the end. How specific is this to chocolate? It's really not, because we saw it applies to lava, it applies to eyes, it applies to all sorts of stuff. Any system with the same physics obeys the same equations. So custard is like chocolate and tears are not really like lava, but you can use the same equations for all of these things. So what have we seen? We have seen a roast ham in which we got an analytical solution after some simplifying assumptions, of course. We've seen Stollen, where we made some simplifying assumptions and got some simulations that were able to tell us something useful without huge amounts of computational resource because we'd been clever with our assumptions. We've got custard, in which we did some in-depth physical modelling to work out what the equations we should be solving are. And finally, we've got chocolate, which was a model for the cooked custard as well, in which I introduced scaling analysis and the power of throwing away the terms that are difficult to use and don't really add anything much to the detail of your solution. And finally, we should finish with mince pies, about which I have no mathematics, but we're just going to go and eat them. Thank you very much.